we're going to look at a couple of applications of quadratic functions, specifically to situations where gravity is acting on an object. So here's our first example. A ball is thrown upwards from a height of 10 feet with an initial velocity of 40 feet per second. And the first question asks, what is the function that gives the ball's height t seconds after it is thrown? Well, you might recall that we've got a general form of this equation that we're going to use for all of these kinds of problems. Okay, it says that the height after t seconds is equal to negative 16t squared plus v sub 0 is the initial velocity times t plus h sub 0 is the initial height. So for our example here, the function is going to start out still negative 16t squared. That part always stays the same. Plus my initial velocity here was given to be 40 feet per second, and my initial height was given to be 10. So here's my function. Okay, then here are some examples of the kinds of questions that we can answer using this function. So first question, when will the ball be 30 feet in the air? Well, that means that we would replace the h of t with 30 and solve for t. So let's do that. Okay, I've substituted 30 for h of t. Now, of course, before I can solve this kind of an equation that has a t squared and a t in it, I need to have it equal to 0. So I'm going to subtract 30 from both sides. And that's going to give me minus 20 for the constant term. And now this thing is probably not going to factor so nicely, so I'm going to go straight to the quadratic formula. So t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2 times negative 16. Okay. Now when you're simplifying the portion under the radical here, notice that we've got 3 negative signs here. So it's going to end up being a subtraction. So you're going to get 1600 here, and then when you subtract off the other part, that part under the radical is going to be just 320. So we have this, and then I'm just going to let my calculator give me an approximation for the square root of 320 to about, usually to 1 decimal place, so usually to tenths. And so when I do that and work out the calculations here, this gives me 2 different solutions. Approximately 0.7 and the other one is 1.8. Okay, so let's think about what that means. Remember, t is the number of seconds after this ball is thrown. It was thrown upwards, so it started out at 10 feet, but then it went higher, and at some point it was at 30 feet. So at 0.7 seconds after it was thrown, it was at 30 feet. And then again, 1.8 seconds after it was thrown, it was at 30 feet again. Why would it be at 30 feet twice? Well, let's think about the graph that would go along with this function right here. Okay, remember it's a quadratic, it's a parabola. Okay, and when time is 0, when t equals 0, that's our initial height, so that was 10 feet. So it started out there, but it was going up, and then at some point it reaches its maximum and it turns around and comes back down again. So what we've discovered is that it was 30 feet in the air at 2 different times. Right? So let's say this is where 30 feet is. We're just kind of using a rough sketch to get the idea here. This would be at 0.7 seconds when it was on its way up. And this would be when it was on its way down. So it was at that height twice. Let's see, what was that second value? 1.8. Okay. So that's why there's two solutions there. It was actually at that height at two different points in time. Then the second question that we can consider is, when will the ball reach 40 feet? So this is basically the same procedure. I'm just going to replace the h of t with 40 this time. Okay, and again I need to subtract 40 from both sides so that I have 0 on one side of my equation, and then substitute into the quadratic formula. This time when I substitute in, I'm going to find I have a little bit different outcome. When I simplify the portion under the radical this time, I'm going to end up with a negative number. Okay, so I'll get negative 40 plus or minus the square root of negative 320 over negative 32. When I encounter this situation where there's a negative under the radical in the context of a word problem like this, it means that whatever question I was trying to answer is actually impossible. It will never happen. Okay, so I'm just going to put this symbol there. That means I've reached a contradiction. This can't happen. Or I might write no real solution. Okay. And in the context of the word problem, it means the ball never reaches 40 feet. Okay, so thinking about my graph again, that must mean that 40 feet must be up here somewhere. Okay, at some height that the ball never gets to. Okay, so that maybe brings up the next question. We'd like to know what that maximum height is. How high does it go? Turns out that it's easier to first figure out how many seconds it takes to get to its maximum height, and then from there we can figure out what the maximum height actually is. You might recall that the vertex of a quadratic, or a parabola, has its, we usually say x-coordinate, here it's the t-coordinate, but it has its horizontal coordinate at negative b over 2a. Okay, that we were able to kind of figure this formula out by thinking about the quadratic formula that gives us the x-intercepts here and here. And it turns out that this will always tell us where the vertex or turning point or max-min, in this case maximum, occurs. So let's do that for our function. So it's going to reach its maximum height when t is equal to negative b over 2a. Negative b would be negative 40. 2 times negative 16. And that turns out to be 1.25 seconds. Okay, so that's when it reaches the maximum height on my graph right here. That's the x-coordinate, the t-coordinate of the vertex. How do I find that actual height? How do I find this value here? Well, remember that this is h of t, right? And we have a formula for h of t. This was t. We've got a way to calculate that. If t is equal to 1.25, I can just substitute 1.25 for t here and here, and I will find the height. You'll really definitely want your calculator to do this. So let me just move this so you can see a little bit better. Okay, what is the ball's maximum height? I'm going to substitute 1.25 for t. So that is equal to this calculation. Okay, and when I punch that through the calculator, it turns out that that is 35 feet. So that's the maximum height that it attains. Notice that letters D and E are asking slightly different questions, and so you need to make sure that when you're doing application problems that you're answering the correct question. So in letter D it says, when will the ball reach its maximum height? That means we're looking for a t value. I'll use negative b over 2a and find out when, after how many seconds. the ball reaches its maximum height. Then in letter E, it asks what is the ball's maximum height, and to find that I need to substitute in the time that I found into that formula for height. So I did that to get the number of feet off the ground. And then finally in letter F, it asks when will the ball hit the ground. So thinking back to our formula here, that means I want to know when this h of t here is equal to 0, since ground level would be a height of 0. Okay, so I'm going to substitute 0 for that and solve. So again, quadratic formula one more time. This time I'll have just a slightly different calculation under the radical. Let's see, t is equal to negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. Notice under the radical this time I have just 2 negatives. So that's going to end up being plus a positive. Okay, so just notice that when you're simplifying. So I come out to negative 40 plus or minus the square root of 2,240 over negative 32. This is going to give me 2 solutions, but I'm going to have to interpret what those mean. Again, I just let the calculator help me approximate and round to the nearest tenth. So the 2 solutions I got are negative 0.2 and a positive 2.7. Well, remember that t is time, and it's specifically the number of seconds after I throw the ball. So a t-value of negative 0.2 doesn't really make sense, because that'd be like negative 0.2 seconds before I started this whole experiment. So this is going to be my answer. I'm going to say 2.7 seconds after the ball was thrown is when it's going to hit the ground. So those are examples of the calculations that we would go through. Just one last look at this graph here. Notice that what I just found, that point where the ball hits the ground, is this x-intercept right here, and the negative 0.2 that I discarded would be the other x-intercept over here, just a meaningful interpretation in the context we were in. Now there's one variation that I wanted you to see with these gravity problems, and that is the situation where instead of something being thrown, it's actually just dropped. Okay, so here's an example of that situation. This time my ball is dropped from a height of 60 feet. And so we want, again, the function that gives its height after it's dropped, and then we're going to ask how long it takes to reach the ground. Well, when something is dropped rather than thrown, I'm going to try and straighten this out, it means that its initial velocity, that v sub 0, is equal to 0. So thinking about our general formula, the negative 16t squared remains the same, and we have an h of 0, we have an initial height of 60 feet. But this term right here is going to disappear because v sub 0 equals 0. Okay, so my specific formula for this situation is just this, negative 16t squared plus 60. And that means that answering this second question, how long will it take the ball to reach the ground, I'm not going to have to use the quadratic formula, because reaching the ground is when h of t is equal to 0, so I'll just substitute 0 for that. And when I go to solve this equation, since there's no t term, I can just take the negative 16t squared over to the other side of my equation, divide both sides by 16, which that simplifies a little. That's 15/4 or 3.75. And then take the square root of both sides. Again, the theoretical solution would have 2 possible square roots, plus or minus the square root of 3.75. Since we're in a context, let me just go ahead and get the approximation is 1.9 seconds, but again, since we're in a context where t, time after the ball is dropped, we are going to end up discarding the negative answer here and just say a positive 1.9 seconds after it's dropped is when it's going to reach the ground. If we want to think about what that graph looks like, it would just be a little variation of the other graph. Here's the situation. Okay, it starts out at the highest point that it ever reaches. Since it wasn't given any initial velocity pushing it up any higher, it's just going to simply fall from its initial height of 60 here. And we're just finding the 1.9 seconds. We're finding how long it takes for it to reach the ground. So that's the variation that you may encounter when you're looking at some problems that relate to how gravity acts on objects.